Hi all, welcome to this week's physics seminar. As you know, this is one of our last in our this semesters, so let's enjoy it as much as possible. So, we have the great pleasure to host today Chih Chien from University of California, Merced. Let me say a few words about Chun. So he did his bachelor and master degrees in the National University of Taiwan. Then he moved for a PhD in physics in the University of Chicago, so very close by. Then he moved for a postdoctoral research position at the National Laboratory, Los Alamos, where he had the prestigious Oppenheimer postdoctoral fellowship. And finally, he moved to the University of California, Merced, where now he's an associate professor in physics. His research interests lie at the interface between theoretical atomic, molecular, and condensed matter physics. His focus is placed on superfluids and superconductors, non-equilibrium dynamics of full-coupled atoms, trans-energy transport molecules, and high quantum hybrid atom systems using full-coupled atoms, of course. So today he will talk about atomic Fermi superfluid and spherical bubble, BCS to BEC crossover, and vortex structure. Thank you very much for being here. The stage is yours.
Thank you for the kind introduction. Can people in the back hear me? Good. Okay, then I don't need to wear the microphone. Okay, so today I'm going to talk about something that I've been working on recently on this spherical bubble trade potential. So as Simon introduced, I'm from University of California, Merced, and that's the 10th campus and newest one in the UC system. So it was built in 2005, and you can see that this is a map of California. And if you put a pin at the epicenter, then you are not going to miss Merced. So we are close to Yosemite National Park, and we are called the gateway to Yosemite National Park. So if you visit Yosemite, you are welcome to stop by Merced. And we are also close to the Bay Area and other places. We have a rapidly expanding campus. So right now we have almost 10,000 students, but we are still growing. And the work that I'm going to talk about today, it was done with Hao Guo from Southeast University and Yan He from Sichuan University. And part of the work was funded by NSF. So this is the outline of the talk. And as usual, I need to, because of the nature of the talk, I need to play this warning sign that there will be mathematical and abstract concepts, so viewer discretion is advised. Okay. And first, since Simon told me students are in the audience, so I will give a brief introduction to what are those atomic gases and how can we have superfluid in them and what can we study. And then I will introduce this funny concept called BCS-BEC crossover and the difference in 3D and 2D systems. And then I will introduce this recently realized bubble trade technology and what can we study using such a geometry. And one topic, two topics that I'm going to talk about. One is that we can see that there are actually two ways to introduce this crossover. And then I will talk about something called quantum vortices. So those are excitations in superfluids. And what can we study about that? And what's funny is that if I have time, I will explain this to you that mathematically those vortices, they actually look like topological insulators. And there have been lots of studies recently about those topological systems. And if I still have time, which typically I don't, okay, then I will mention lattice systems on spherical system. And typically, our basic colloquial to start with spherical curve, okay? Sorry for those in the audience who already know this, but the story goes like this. So say a farmer found that his cows or her cows are sick, okay, but no vet is available. So desperately, the farmer is a physicist. So by looking at those cows, the first sentence coming out of the physicist is that, well, let's assume all those cows are spherical, okay? But today we really have spherical objects. So like, I'm not just joking, okay? And to make the problem a bit more interesting, we are not just talking about solid spheres. We are talking about bubbles. Okay, bubbles has empty inside and empty outside. Okay, but there is a thin layer that forms the shell. Okay, so when I was a kid, and also my kids, they love to play with soap bubbles, right? And for some reason, like there are less the gum available nowadays. There are less in this kind of like big bubble type. But when I was a kid, I can do something like this. Okay, but typically the fun start to die when physicists come in, right? Because they will say, "Oh, look at this! Like there must be a surface tension, right? Okay, let's calculate the potential difference." Okay, now we understand more. Okay, about those things. So today I'm going to kind of show you that experimentally people can realize a bubble almost about millimeter size, and they are made of atoms. Okay, and what can we study there? But first, let's kind of learn a little bit about atomic physics. Okay, particularly this ultra-cold and controllable atomic systems. So what happens is experimentally, it's possible to get a collection of atoms, and then by using this laser cooling technique, okay, so they can reduce the kinetic energy of those atoms. As a consequence, those atoms become very, very cold. Okay, how cold can they be? Like nanokelvin, that kind of low temperature. Okay, so they are basically motionless. But even though they are motionless, if you don't do anything, they will still fly away eventually. So what happens is people need to use either magnetic or optical potential to kind of hold them together. Okay, so that's why typically you will see something like a potential, like a ball that holds those atoms together. And in this world, okay, there are two types of atoms. So there are bosons and there are fermions. Okay, the difference between them is this: bosons, they have no problems sitting together. Okay, so what that means is you can have two identical bosons and they are using the same quantum description. Okay, the same quantum state. You cannot do this to fermions because there is a famous principle called Pauli's exclusion principle. It says you cannot put two identical fermions, okay, in the same quantum state. Okay, so as a consequence, if you have non-interacting free particles, at low temperature, bosons, they try to minimize the energy by going to the lowest energy state. So more and more bosons go there because they can sit together peacefully. Okay. Eventually, you get a macroscopically coherent, big many bodies quantum state, and that's what's called Bose-Einstein condensation. Because most of the bosons they condensate into this lowest energy state, and experimentally that has been shown by taking pictures in momentum space. So what happens is the lowest momentum space state happens to be the lowest energy state. So by lowering the temperature, you can see that almost all particles squeeze toward the lowest momentum or lowest energy state, form a sharp peak. Okay, so that peak is a signature of this phenomena called Bose-Einstein condensation. For atomic systems, it was first realized in 1995 by Cornell, Ketley, and Wyman, and they got Nobel Prize, Physics Prize in 2001. So that's the story for bosons. Professor Statistics is the world expert on bosons. Okay, I feel very uncomfortable talking about bosons in front of him. So today I'm going to focus on fermions. Okay. Fermions, on the other hand, they don't like each other. So what happens is that they will, if there is no interaction, they will simply pile up, okay? And they form something called a Fermi sea. So they just pile up, okay? And how can atoms have interactions? So that what happens is, semi-classically, you can think of them as tiny balls. So they can hit each other. That's what we call collision, okay? So they can have interaction through collision. For bosons, that's not a problem. They can just hit each other. For fermions, they actually create a problem because space, okay, position is also a quantum number. So if you have two identical fermions, they don't want to be in the same position, but they have to hit each other to have interaction, right? So if you only have one species, one component of fermions, identical fermions, they don't interact with each other. But then that's not a problem for experimentalists. What happens is because atom has many internal states. So what people can do is they put atoms in two different internal states, what we call hyperfine states. Okay, so two different internal states. Now they have an internal label, just like spin up, spin down. Okay, then now they can get away with Pauli exclusion. Now spin up can hit spin down fermions, and they can have interactions. Okay. And by using magnetic field, they can control the interactions. So they can have both either attractive or repulsive interactions. Today, I will focus on attractive interactions. Why? Because if you have a very, very strong attractive interaction between two types of fermions, you can kind of glue them together. And okay, if you glue two fermions together, you get a composite boson. So what happens is, if you get composite boson and if you pull it down, you will get a boson condensate of composite boson. And that's exactly what happened. So turns out, along this direction, people don't pull it down. It's already very cold. What happens is, say experimentalists, they just increase the attractive interaction. When the attractive interaction is so strong that the two fermions, they form bound states and they behave like composite boson. They will give us a peak of boson condensation of composite boson. Okay, so you start to see that, well, fermions, they need to do this pairing tree before they can do more interesting things. Now, the pairing actually was not first discussed in atomic system. It was discussed in the context of superconductor because electrons first show those very interesting behavior. So a bit of history of superconductors. So the first superconductor was found back in, you believe it, more than 100 years ago, people already did this, right? So Einstein found superconductors, and then in a couple years later, he got Nobel Prize. But so what constitutes a superconductor? The first thing is that people observe that they can support what's called supercurrent because there is no energy dissipation, okay? And as a consequence, there is zero resistance. But we need to be a bit careful, okay? Because later it was shown that, well, there is a second effect called Meissner effect about magnetic field repulsion that we also need to check, okay? But so after the discovery, it actually took theorists 46 years to figure out what happened, okay? And I was told that a good talk should mention Einstein because Einstein is so famous, right? We have Einstein in this talk, okay? But in a bad kind of situation, because believe it or not, Einstein proposed a theory for superconductor. It's called molecular chain theory. It was recorded in this book, okay? Of course, it didn't work, okay? And three people from Cooper's river, and that's why we see this BCS name, okay? They actually found what happened in Fermionic system. So what happened is electrons have spin, so spin up and spin down due to this vibration phonon coupling. They will form what we call Cooper pairs. Okay, and once they form Cooper pairs, they will start showing those interesting behavior. And I was told that Cooper actually was high energy physicist. So this is an interesting example that an integration of high energy and the condensed matter physics will come out something very powerful and very important. Okay, so pairing will lead to Cooper pairs, and those Cooper pairs start to show those macroscopic quantum behavior. For atomic system, it's a bit later. So helium-3 atoms, people actually can show that they also form superfluids, and helium-3 are also fermions, but they are charged neutral. So what they form is superfluid, not superconductor. Okay, and the three major contributors, they got Nobel Prize much later in 96. Okay, so how about this? Let's have a naive picture of what happened. So what happened was that if you have a attractive interaction between two species, okay, two internal states of fermions, then if the attractive interaction is weak, they kind of form very loosely bound, far away pairs, okay? And those are Cooper pairs in the conventional sense. But if we can increase the attractive interaction so that it becomes so strong, then each spin up will find a partner of spin down, and they are tightly bound, okay? And they form like composite bosons, and then they will behave just like bosons to exhibit boson condensation. Okay. This picture, again, was actually proposed back in 69. And then again in 80, people formulated, kind of revisited it again. Turns out, if this is possible, if the attractive interaction can get so strong, then what happens is the density also needs to be modified. So it becomes a couple equation theoretically, okay? And what happens is that the pairing gap that kind of characterize how strong are the pairing between up and down. The pairing gap will keep increasing while the chemical potential will keep dropping, and it will eventually become negative. So what is chemical potential? You can naively think of chemical potential as the energy that you get or you lose if you put more particles. And why do we get negative chemical potential here? Is because once particles form bound states are kind of deep down in the energy spectrum, right? So we kind of lose energy on that front. And that's why, say, if you see negative chemical potential, that means some kind of bound states are strong in your system. So that's the BEC side. And then if chemical potential is positive, then they are still far apart. Then those are, if that happens, we call it the BCS side. So BCS, BEC, and there is no transition in between. It's just a smooth behavior. So people call it crossover. So the crossover actually has been realized experimentally, say in early 2000. So what happened is by tuning the magnetic field, we can control the collisional properties of atoms, and we can translate that to the attractive interaction between atoms. So what happens is if the attraction is weak, we are on the BCS side, and then if the attraction is strong, then we are on the BC side. How do we know if we have superfluid? So what happens is we can rotate the system. So if you rotate a bucket of water, okay, you see the surface of the water will deform, right? But if you rotate a bucket of, not a bucket, okay, a piece of superfluid, then you will see those tiny points. They are actually tiny spirals with circulating current, okay? Those things are called quantum vortices. So if we can show quantum vortices, then it's a proof of superfluid, okay? So it has been shown that, well, we can realize this, and then we can show that they are superfluid. Moreover, by checking the spectrum, they actually can show that, well, there is really an excitation energy somewhere in the system, because you will see like two peaks, and the distance kind of tell us how much energy do we need to put in to break them, okay? So, by the way, later I will have more discussion of quantum vortices, but quantum vortices is another important topic in physics. So you can see that these three, they study superconductors and the vortex physics, and they also got Nobel Prize in 2003. So lots of focus has been placed in those things. Now, before we really dive into the details, let me explain a little bit how this, why the interaction can be controlled. So the interaction comes from collisions of atoms, right? So, and magnetic field will affect how they collide with each other. So by changing, by imposing a magnetic field, we can push those atoms near something called phase bar resonance. As a consequence, okay, the attracting interaction will become stronger and stronger. Eventually, they will form what we call two-body bound states. So in textbooks, there is a concept called two-body S-wave scattering length. That's actually a good indicator whether we have direct two-body bound states or not. In the sense that if this thing is negative, then we have a trading interaction. If the scatter length A is positive, okay, what happens is that you can check the textbook. They will tell us, oh, okay, that's because you have a bound state, okay, two-body bound states below your spectrum, okay. As a consequence, then your scatter length will change sign. So experimentally, people try to measure this number of scattering lengths and kind of know that, okay, whether there is a bound state hidden in the system or not, okay. And for 3D, this is actually a very powerful method to determine whether we are on the BCS side or BC side, because on the BCS side, there is no genuine bound state, so scatter length should be negative. On the BC side, because we have bound states, so scatter length should be positive. For 3D, okay, people use this for a while, but people start to realize this method is not very good in 2D. Why? Because if you solve two-body scattering problem in 2D, we always get a bound state, so we are always on this region. But it doesn't mean that we cannot form Cooper pairs, okay? It just means, well, the two-body scattering always has a hidden bound state below there, okay? So what happens is the scatter length is always positive, and the pairing energy is no longer, we cannot cheat. We cannot just look at the scatter length and say, oh, I know you are in the BCS or BC. No, now we need to check the two-body bound state. And from the two-body bound state, we can kind of do a reverse to know if we are on the BCS or BC side. Okay, that's a slight complication. Anyway, experimentally, two-dimensional crossover has been done by using this pancake shape cloud. Okay, so on a plane, and you can see that, well, when the interaction gets stronger and stronger, we get a peak of composite bosons because now we bind different two-component fermions tightly, okay, and they behave like composite bosons. And to check if we really have superfluid, what happens is people will just disturb the system by using a potential with velocity v pushing the superfluid. If the superfluid does not follow your pushing, we are in the superfluid regime. If you see a current following your pushing, that the velocity perturbation destroys your superfluid. That's what people call the critical velocity. And by checking if there exists a region with critical velocity, people can establish that, okay, for those kind of experiments, we really have superfluid, okay? Just to convince ourselves that there are superfluid. There are actually other places people are talking about BCS-BEC crossover. So for example, for these iron-based superconductors, what happened is by mapping out the excitation spectrum, the authors claim that, well, the changing of the excitation spectrum actually feed into the changing spectrum from BCS behavior to BC. So they are claiming that very likely, okay, very likely, the Cooper pairs are also doing similar things in this material. And also they can have other type of more complicated device, and then they use gate to control the gate voltage to control the chemical potential. And they can make out something that's similar to the crossover. So it's not just atomic physics. We can see this in other places. But today I'm going to talk about a new chapter here, okay? So some of you are working on astrophysics or know or heard about this, like there is a giant structure out there in the space, right? It's called International Space Station, ISS. It was launched. Can you believe it? This, like, it was launched back in 1998, okay? And then, say, people can start doing experiments there. So after so many years of renovation, nowadays, it's possible to put all those equipments to generate those, like, ultraviolet atoms in a size that's probably smaller than a compact car. So what happened was that in 2018, they sent a set of equipment. The Jet Propulsion Laboratory lead this effort. So they sent an equipment to the outer space, to ISS, to do some coherent experiments. And you might wonder, like, what experiment can they do? Okay, they did this bubble trap. Okay, in a minute we will see what's the reason they must do it in outer space. But they want to realize this spherical bubble trap in the sense that we have atoms only on a thin shell, nothing inside, nothing outside. Okay, how can it be done? So back in 2001, so 17 years before they launched this coherent experiments in outer space, people already thought about maybe there are some ways to realize this. And here is a more concrete way to do it. So what happens is you have to have minimal 2 internal states, and one state lights your laser light. So you have laser lights shining on the atom, right? So one state lights your laser light. So it will go toward where the light is strongest. Another internal state don't like laser light, so they try to fly away. Okay, so you have one up, one down. Now, the separation between them are typically in the range of radio frequency. So then sending radio frequency, trying to mix the 2 levels so that the upper branch goes down, the lower branch goes up. Okay, and in most systems, unless you have very weird symmetry or constraint, in most systems, if you have 2 energy states trying to cross each other, something called avoid crossing will happen. So what happens is the energy actually bend a little bit to avoid touching each other. So they will bend like this. Okay. Now, if you put atoms on these 2 points, okay, so they become 2 separate points in real space. But experimentally, the laser light actually surrounds the whole cloud. So what happens is now you can rotate this thing all over the space because everywhere you see laser light, right? So if you rotate 2 points in the whole space, you get a thin shell. Okay, so nothing inside, nothing outside, but only atoms on the thin shell. Okay, theories are usually too naive. Whatever is for realistic system, the minimum they can experimentally can find, they have a redundant, not really redundant, it's always there. Like a third state, it kind of mix a little bit, but it doesn't destroy the picture, luckily. Okay, so eventually we can still have this wall, and then in 3 dimensions, it will form a bubble. Okay, this is what happened in the International Space Station. Of course, it doesn't look like a perfect sphere because they have problems with laser, etc. So it's a bit elongated, okay? But at least in principle, this becomes demonstrated. Like we can have a thin cloud of atoms, nothing inside, nothing outside, but only the shell. Okay. Now, what happened? Like, why do we need to spend so much effort to send this to outer space? It's because the atoms are heavy enough in the sense that if you try to do this, okay, so you can read the paper, they have 5 prints. Like if you do this on Earth, okay, then it will collapse. You never get a beautiful shell, okay? So that's why they try to do this. At this point, they realize Bose-Einstein condensation. Bosons already on the shell, and there are lots of theoretical analysis of what kind of properties will be on the shell. But once we have Fermi bosons, the next stage is to discuss fermions, because fermions are more complicated in that sense. So theorists will lead the effort this time. Okay, so there is rendition of Fermi case. We start to realize this is not an easy problem. Why? Because back in quantum mechanics, we know that now you need to deal with spherical harmonics, and the energy will become L times L plus 1, the total angular momentum. So we start to get stuck in all those complicated structures. Now, to make life more miserable, we can add interactions. Okay, and interactions will depend on your quantum number. So the angular momentum number and the z directional angular momentum number. And then even worse, there are conditions that, well, this system is rotational invariance, right? So the incoming M1 plus M2 needs to be the same as outgoing M3 plus M4. Okay. While you feel like desperate, we need to build BCS theory on a sphere. Okay. BCS theory was proposed back in 1957, right? So I say, when I start thinking this, I thought that, well, if I just survey the literature, I'm going to find solutions. Then I'm just going to cheat. I will use them. Okay. After months of search, we couldn't find any attempt. Okay. So there are BCS solutions on solid sphere, but there is never BCS solution on a shell, a spherical shell. Okay. So someone has to do the first work. And unfortunately, that will be me and my collaborators. So we decide, since we are the first, right, we can say anything we want. Okay. So if you read it, yeah, so try something that's like no one explored before. So BCS theory says you can have spin up and spin down fermions, okay, and then they form a pair with zero total momentum. So if you have plus k fermion, then you will pair with the minus k fermion, so that the center of mass momentum will be zero. How can we translate this to a sphere? We can say that, well, then if we have pairs on a sphere, then they will prefer the zero momentum state. They will dramatically kill like lots of blocks in the Hamiltonian and in the calculation. Okay. And then we can even use, okay, I don't want to bother you with this, but use some theorem from quantum mechanics to further reduce that so that eventually become a manageable problem, just like the BCS theory. And we can use the standard method for solving BCS theory. It's called the Bogoliubov transformation, and then we can diagonalize the Hamiltonian. Okay. Afterwards, we will have what we call equation of motion. What do they mean? It means if you know the physical parameters, you plug them in, it will give you measurable quantities like the pairing gap or density. Okay, and so we can use this collisional model to relate the interaction and the scattering length that can tell us where we are. Okay, I know. Like after all these tortures, okay, I probably lost everyone except Professor Don't tell me you got lost. Okay, but no worries. Even Alexander the Great lost all his company. So after he conquered so many lands, okay, his soldiers were exhausted and homesick. So they decided to tell Alexander the Great, it's enough, okay? And I guess this is the case right now, okay? So to release you a little bit, okay? Now, how about this? Let's take little pictures. So think of them as tiny balls. Fermions are tiny balls, but they have attractive interaction so that they tend to bind together, okay? And what happened is this. So I was told once that, say, if you can fully understand, probably not 20 years, okay? If you can fully understand what I did in the past, probably 7-8 years, okay? In this 15 minutes talk, then usually there are two possibilities, okay? So either I'm an idiot, which is very likely, okay? Or you guys are genius, which is even more likely, okay? So instead of dwelling on those details, how about this? Let's follow this rule of thumb, shut up and calculate, okay? And we will just focus on the results from this point on. So fermions are tiny balls, they can attract each other. The attraction are tunable, okay? That's the rule of thumb. One last check before we start checking the results. So we know that on a big enough sphere, okay, locally, we cannot tell the difference between a sphere and a plane. And that's true, right? Because the Earth is sphere, but locally we don't, well, we feel like it's plane, right? So final check, sanity check. Let's write down the equation for fermions on a shell, okay, versus the equations for fermions on a 2D plane, you start to see, right? They resemble each other. So that's kind of assurance that we are not making trivial errors. Okay. So, like I said, we can increase the trading interaction to find the fermions, right? So they will go from BCS to BEC. And how do we know there is a crossover? Let's check the chemical potential, right? So you can see that, well, by increasing the trading interaction, the chemical potential start to drop, and then at some point here, right, it changes sign. So by increasing a trading interaction, we can have a crossover. And people will say, well, this is so trivial. Like, why do you want to spend all this effort just to show something that already happened? Right? Okay. Now, here comes a funny thing that cannot be done in 3D. So what happens is, if you have a cloud of fermions, right? Now you make the cloud smaller and smaller and smaller. Okay. Smaller and smaller and smaller. You start to see that its chemical potential will start to increase. And then at some point it crosses zero. So it's kind of weird. You don't change interaction. Okay. Same interaction. You just make your cloud smaller and smaller and smaller. Okay. You cross the crossover from the BEC side toward the BCS side. Weird, right? Like, but we didn't change the interaction. What's going on? Okay. What's going on is this. Now, the difference is on a sphere, we have a finite system. Okay. So if you make it smaller and smaller, the density will increase. So what happens is, if you calculate the ratio between kinetic energy and the pairing energy, okay, the kinetic energy is determined by the Fermi energy or the highest angular momentum state you can go. On the other hand, the pairing energy, didn't I say that I will fix interaction strength? Right? So kinetic energy will increase when you make the ball smaller and smaller. And the kinetic energy will work, try to push particles away. Even though the size is smaller, okay, but it has higher kinetic energy. So what happens is, then you will push the particle toward the BCS side. So weaker pairing in that sense. So sometimes we say weaker pairing, smaller pairing, but that's not totally true. What we are saying is, compared to the kinetic energy, the pairing energy is less important. That's what's important. Okay. So by shrinking the size of the sphere, okay, we are not changing the interaction energy. We are bumping up the kinetic energy. Okay. So but the ratio will help us to push the system across the BCS-BEC crossover. And why is this not possible? Because we need to go back to the 3D case. 3D case says that the sign of the scattering length actually determines where you are. So by squeezing a system in 3D, you are not going to change your scattering length, the sign of your scattering length. So you cannot do this trick in 3D. So you have to do it in 2D. So that's condition one. Condition two, you need to do it in a compact system so that when you change the size, your particles will not escape. Okay. So this bubble trap happens to be a very good place to do this. If you are confined to this system, it's possible to do this, but then you will encounter certain boundary effect. A sphere, there's no boundary. Okay, that's supplementary. Okay, final sanity check from the theoretical side. I kept claiming superfluid. How do we know? Okay, at least from the theoretical view, how do we know we have superfluid? Actually, people formulate this long ago, and it's well documented in standard books like Fermi and whatever. So what happens is that there is I'm not going to torture you with this, but there is a well-defined procedure, and then you can calculate how much fraction of the density will exhibit superfluid behavior. And the ground state, the BCS solution, indeed has full density in superfluid state. So final sanity check, like I didn't make trivial error in the sense that they are real superfluid. Why do I insist they should be superfluid? Because then we can study quantum vortex. Okay, quantum vortex, they are called tabulation excitation in the sense that you rotate, then you trade angular momentum inside. Okay, so then if you go around, so they are tiny spirals with current. If you go around them once, you get a 2-pi phase. Okay. Here comes a very funny difference between BCS and B. So I say it's a smooth crossover, right? But they have an intrinsic difference in the sense that inside a vortex core, okay, if you have BC superfluid, BC type, okay, then the order parameter which characterize the superfluid will drop to 0, while the density will also drop to 0. So the density will go with your superfluid inside a vortex core. Okay. BCS superfluid, on the other hand, they found a way to kind of fill up the core in the sense that, well, since we are loosely bound and a vortex is rapidly rotating, how about this? Let's break some Cooper pairs and just put single unpaired fermions in the inside. Okay, so what happens is for BCS system, the pairing will tend to go to 0, while the density does not. Okay, so that's a very big difference between BC and BCS. On the BC side, if you want to kill superfluid, because they are tightly bound, if you want to kill superfluid, you repel all your particles away from that vortex core. On the BCS side, they are weakly attractive, so you can break them and put some paired fermion at the center, okay, while all other Cooper pairs surrounding them and rotate, okay. So that's kind of known picture. Now, what happens if you do this on a sphere? If you rotate, okay, it's kind of funny. Like people know about this, but say we notice that I use vortices, right? On a sphere, turns out you cannot get less than 2 vortices. Why? Because there is a mathematical theorem called Poincaré-Hopf theorem. So it says if you sum up one mathematician called the index of singularities on a surface, okay, on a 2D surface, it has to be equal to the Euler character of that surface. Okay, so what is Euler character? It just says does your surface has holes in it or not? And a sphere does not have any hole, right? So that's a very good system. So Euler number is 2 for a sphere. So according to this, you cannot have less than 2 singularities to start with. And we all know this. You guys know I'm coming, right? So you rotate this, right? There must be a rotation axis. So the North Pole and South Pole, if you have vortices, they will start with that 2 points. So you will not have a single vortex on just North Pole. You will have one on the South Pole to start with. So the easiest case is like this, okay? But of course, you can have more complicated case, but you cannot escape the mathematical theorem that you sum the indices, okay? The final answer should be 2. So people already studied this for Bosonic system. How about fermionic system? How can we study vortices in fermionic system? Then we need to use something called Bogoliubov-Chien equation, okay? So this is just a generalization of the Bogoliubov method to inhomogeneous superfluid system. And I would like to mention Chien. He made lots of contributions in superconductors, but later he moved on to soft matter physics. And he actually got a Nobel Prize for his contribution to polymers and liquid crystals. But the equation that we are going to use is this. So anyway, treat it as a black box that you can put on the computer so that we can solve this to get vortices. Okay? What do we get? So remember that locally, a sphere is not that different from a plane wave. So if we only have one unit, so mu is the unit of angular momentum. If we only trade one unit of angular momentum inside a vortex, what happens is you can see that the superfluid will disappear inside the core. So the core is here. This is the North Pole. Okay. The density on the BC side will drop almost to zero. Okay, there is numerical error. But BCS side, the density will not drop to zero. Just like I said, because on the BCS side, they found a way to cheat. They break pairs, put some unpaired fermions there. Okay. And you may say, well, that looks very interesting, but can things be even more interesting? Okay. If you trade 2 units of angular momentum, now what happens is the core become bigger, right? Because you need to accommodate bigger angular momentum. Now here comes the thing. The unpaired fermions will be too many. As a consequence, instead of showing a peak inside the vortex core, we actually see a peak. Okay. Why do we have a peak? It's because, say, the fermion system say, well, now you rotate so fast, we break lots of core pairs and dump those unpaired fermions into your core, that we see a density peak. Okay. So 2 units of angular momentum. Who wants to guess what happens if we have 3 units of angular momentum? So 3 units of angular momentum, we also see a peak. We also see that now inside the core, the rotation is opposite to your superfluid flow. And why is that? In the next slide, I will have more details. But turns out those broken fermions, they also carry angular momentum. And as a consequence, they don't rotate the way your paired superfluid does. Okay, so what happens is now we have a core with normal fermions rotating counter to your superfluid. And that's only possible if you have enough angular momentum inside your system. And this was actually conjectured a while ago. And we show concrete calculational results to confirm this. What happened was this. So we can output all the energy spectrum. You see that on the BCS side, there are actually low energy states. Because for M is the Z directional angular momentum quantum number. You see that we have states that carry angular momentum, and they are in low energy. Why do they sit in low energy? Because they are inside the core, right? So they are not participating in this superfluid part. Okay. The current follow this is the current follow this expression. So it depends on those states. So those states, even though there are only a few states, but they are highly concentrated inside the core, and they carry angular momentum. As a consequence, this is what we saw, right? So we saw counter flowing of currents in it. Okay. Now, for those who take a look at those states carefully, you see that for 1 unit of angular momentum, there is kind of 1 branch, right? 2 units of angular momentum, we kind of see 2 branches. 3 units of angular momentum, we see 3 branches. Okay, so is it a coincidence or is there a deeper reason? Okay, so turns out if we just take a low energy sector, okay, so just do this low energy approximation. The Bogoliubov-Degen equation, okay, the Hamiltonian part in the low energy sector can be written in terms of the Pauli matrix. So sigma 1, sigma 2, sigma 3, there are 2 by 2 Pauli matrices. Okay. And if you check the literature, there is a famous model called QWZ model for 2D Chun insulator, and the Hamiltonian can also be written in terms of sigma 1, sigma 2, sigma 3. You start to see the resemblance, right? So, what is a Chun number? Okay, Chun number is actually nothing mysterious. It says if you can write a Hamiltonian in terms of sigma 1, sigma 2, sigma 3 of your Pauli matrices, then you can collect the coefficients in front of them and treat it as like a vector, a fictitious vector, okay, of the coefficient. So what happens is for a periodic system, we have this concept called Brillouin zone. So the Brillouin zone in 2 dimensions is a 2-dimensional surface, periodic closed 2-dimensional surface. And then this vector, the tip of this coefficient vector, you will form another surface here. So you have a mapping from two-dimensional green zone to a sphere. So in mathematicians' brains, they can read this object around this. Okay, I cannot, but mathematician can. Okay, so they say, well, how many times the second or target space wrap around your original space is called the Chien number or just the rating number. Okay, so if we have that understanding, we can go back to collect the coefficients from the Lorentz energy approximation of the Fermi equation. And then there is a well-defined formula to figure out the rating. Okay, so we just plug in, and then turns out that number is just a winding number. So in other words, this mapping is kind of good. Okay, what that says is in topological insulators, people know about a theorem called bulk boundary correspondence. So if you have integer topological index with theoretical system, it will be equal to the number of localized, what they call H modes, so those low energy modes. Okay, as boundary. So what happened is, in that sense, because of this mapping, okay, the vortex happened to kind of borrow the concept from topological insulator, 2D topological insulator. So there is indeed, according to this, there is a one-to-one correspondence between vorticity and the number of branches. So as I promised, So there are experimental progress toward making those high angular momentum vortices. But so far, we encounter a very big challenge in the sense that the excitation energy actually is proportional to the angular momentum square. Okay, so you can do the math. If you want 2 unit angular momentum state, the energy will be 2 square, which is 4. It's bigger than 2 single vortices. Okay, so what happened is experimentally they all suffer this drawback that they can rotate the cloud really hard to get some 2 units, but then after a while it will break into 2 single unit vortices. Okay, there is high hope that the high angular momentum vortices will become stable. Okay, on a sphere. Why? Because there are symmetries to protect them. So hopefully, like with the realization of spherical bubble trap, then we can study this phenomenon. So as I promised, I have no time to talk about lattice. Okay, so it's kind of take-home exercise. Think about this: how can you put a lattice on a sphere? Okay, turns out mathematicians will hit us hard. They will say, well, you cannot put more than 20 points to form a regular lattice. Why? Because it's constrained by geometry. Okay, so there are ways to get around this, but you guys probably need to invite me back in another year to talk about it. Okay, so here is a summary. Hopefully, I show you that well by considering a new geometry and with interacting quantum systems, then we can kind of explore lots of funny things and then kind of find things that are interconnected like the topological systems. And with that, I would like to thank you for your attention and welcome your questions.
Thank you very much, Chun, for this nice presentation. So let's start with questions first from the students, maybe.
When you were looking at those vortices and you go from angular momentum 2 to 3, and the direction that the core is spinning flips, if you were to run a simulation of that and then go from 2 to 3, would that just be an instantaneous change, or is there kind of a time delay in the behavior swap?
Okay, good question. The problem with vortices are that for quantum systems, the vorticity has to be quantized. So you can only have 1 unit of angular momentum or 2 units of angular momentum or 3 units. So what you say is you try to rotate it harder and harder, it will jump. So you will start from 1 angular momentum and then it will become bigger. That means all of a sudden, okay, it means now it has 2 units and then you will rotate harder, it will jump again. That means you enter the 3 units. Right. That's something very interesting, like the power of quantization in this case, right? You cannot have 2.5 in between, right? So you have to jump.
Next question, please. Okay, I have some questions. So, in 2D, we know that the interaction strength has a logarithmic dependence, right?
Yes.
Is this the same for fermions and bosons?
Yes. So
That's why the scattering length cannot go
yes.
negative.
So you can see that actually experimental. So theories know about this, of course. So we put law, right? But take a look at how experimentalists treat this problem. Oh, maybe did I went too far? Yes, here. So experimentalists know the problem as well. Take a look. They also put a log there.
I see.
They know that there is always a bounce, a two-body bounce state below. So A scalar length is always positive. So you have to take log. And the log of that number is actually not a very good indicator of where we are. So they typically need to kind of probe where the chemical potential drops below certain level to call it a crossover.
Okay, I have one more question. So you mentioned that the vortices here essentially do not have fully dipped cores, so they are filled essentially, right?
Yes.
And
But compare fermions will fill the core.
this always happens for fermions. They have a filled notch.
Right, for weak pairing region. This has been a headache always.
And how can I control how deep or how shallow the core of the vortex will be here?
Oh, so you kill the, okay, so take a look. You kill the interactions, like if the interaction is strong enough, then you deplete the density. Here you can see the density is not completely depleted, right? But if you go to deeper BC, then it will be. So like you can kind of tuning the pairing attractive interaction to decide how many fermion pairs will be broken and how many unpaired fermions will be dumped there. Right.
I'm asking because there is a similar phenomenon also for bosons when you have vortices. If you go beyond them in field approximation, you treat, let's say, on the many-body level.
Yes.
The vortices then, due to the superposition, essentially you have a field.
Right.
So you don't
You have, I guess, in your field, and you will call it non-condensed.
Non-condensed.
Right, or excited bosons, right? And but we got a lot of those unpaired fermions to start.
Okay. And the final question that I have, so you mentioned that if you make smaller and smaller spherical cell essentially,
Right.
you keep constant the scattering, right?
So we keep the scattering length fixed.
Yes.
Right.
Yes.
Right. So we
However,
just right.
when you make your system smaller and smaller,
Right.
the effective interaction between them change.
Okay, I kind of so what happened is indeed the interaction will also increase, but it will not increase as fast as the kinetic energy in this case, right? So as it turns out, if you check the ratio, you can see that kinetic energy actually goes much faster than your pairing. So that's how this happens.
Okay, thank you. Good. Maybe.
How does the whole system maintain its shape when it's going through so many interactions, especially in case of vortices?
Okay, so what happens is, remember, the interactions come from hitting each other, right? Collision. So for experimentalists, it's actually not that hard. They just, what's hard is to design the shape of the track. But once the atoms are there, they start colliding with each other. Then they have interactions. And as long as density-wise they are uniform, then the interaction strength is the same everywhere.
So the vortices is that minimum number is 2, right?
Minimum number is 1.
1.
Right.
And then picking the 2
Right. So the vorticity just tells us how many units of angular momentum that got trapped inside the vortex. And then it has to start with trapping 1 unit. And then you rotate faster, then it can trap 2 units, 3 units. But if there is no symmetry and no further constraint, because of the energy is proportional to the number of angular momentum squared, right? So if there is no symmetry, then a 2-unit vortex has 4 times energy compared to 1 unit of vortex. So energy-wise, you are inclined to break into 2 1-unit to kind of save you energy. But experimentally, that's bad for us because then it kind of prevents us to probe those high angular momentum states. And that's why we have high hope. Now, if we put them on a sphere, right, then the symmetry kind of protect us. So hopefully those things will stay longer and we can really see this like 2, 3 higher angular momentum behavior.
And so then the vortices, if you have more than one, do they have the same chirality? And is the short number always possible?
Good question. Say the whole planetary theory only say that eventually they need to add to 2, okay? But there is something called anti-vortex. So you can rotate oppositely, okay? On a sphere, what happens is if you do full-scale simulation, you actually can see you can have sometimes, okay, if you are not project your state correctly, you can have 2 vortices here, but they are the same type. And then you have pairs of vortex, anti-vortex. But then you need to count anti-vortex as -1 in this formula. So if you sum all of them, you still get total number 2. But you can have lots of vortex and anti-vortex pairs on this system.
The reason I was asking because in wild metals, you have wild fermions, which are essentially vortices of very curvature, right? Your vortex is not controlled.
Yes.
And happening there is connected to the fermion. So I was wondering if it's somehow, if you have a vortex and not a vortex, if you have some other thing going on in there.
All right. So here, then this is a constraint from geometry. So it just says if you carefully index them and you sum them, then it has to be 2. Okay. But if you put this on a torus, okay, I haven't figured out. But if you put this on a surface of a torus has a hole in the middle, right? Okay. So chi is 0. That means if you have 1 vortex, you must find an anti-vortex. So that's kind of like geometric constraint. Yeah, right.
Okay. So if there are no further questions, you can ask also our speaker after the talk. So let's thank our speaker again.